Hello and welcome to Minerals, Rocks, and Fossil Talks. I am your geology teacher, Jen, and it's time for some Monday musings. Today, I thought we'd talk about how magma forms and what magma is made out of. Let's start with the inside of our planet, which is full of leftover heat from when it was created, plus new heat from the decay of radioactive elements. However, the crust of the Earth does not float on a sea of molten rock as some models predicted. Molten rock, or magma, only forms in certain places under special conditions. So we've got our different layers of our Earth, and there are only certain places where you're going to find molten rock. One of them is the outer core, but our magma is not coming from the core. That's a lot of other rock to go through. There are other places within the mantle with which magma can form under the right conditions. Now, the upper mantle gets to temperatures comparable to those of lava. However, due to the great pressure with which these rocks are under, it remains solid. So, how can rock melt if the pressure is preventing the melting? Well, we lessen the pressure to keep the temperature unchanged. So here is a model of geothermal gradients that we use to determine just where that point is. So the geotherm is the temperature as a function of depth. The solidus represents conditions at which the rock starts to melt, and the liquidus represents the conditions at which rock completely melts. So if we look here where we have point A and point B, as we go from point A to point B, the pressure decreases a lot, but it only cools a little bit. So it allows the rock to melt. We call this decompression melting. Another way that rock can melt is through the addition of volatiles. Volatiles are substances that evaporate easily and can exist as gases at Earth's surface pressures. Typically, these are water, carbon dioxide, but there are other volatiles that can exist. This will drop the melting temperature of the hot, dry rock and cause it to melt. We call this flux melting sometimes. The third way we can melt rock is by injecting hot magma into the crust. If it has enough heat, it will raise the temperature of the surrounding rock, which may be just enough to melt it. Think hot fudge in an ice cream sundae. We call this heat transfer melting. Alright, so now that we have the how we get the magma, let's talk about composition. What is magma made out of? Well, lots of elements actually. Silica is a big portion. Silica is made of silicon oxygen tetrahedrons, like this one here. But there are also other elements such as aluminum, calcium, sodium, magnesium, and iron. If a magma is considered a wet magma, it will also contain elements that form volatiles such as water, carbon dioxide, sulfur dioxide, nitrogen, and hydrogen. Whereas dry magmas don't have volatiles. It'll just be the first set of elements I mentioned. Now there are 4 major types of magma based on the amount of silica present. These are ultramafic, mafic, intermediate, and felsic. And this is a diagram that you get very, very familiar with when you start talking about igneous rocks. And it shows you just how much of certain minerals you're going to have in each type of igneous rock. Now we're going to take a closer look. So this is an ultramafic igneous rock. Ultramafic magmas have almost no silica in them. They are primarily made of olivine, which is the lighter green mineral, and pyroxene, which is the darker looking mineral. They're ferromagnesium minerals. Some ultramafic magmas will even have a little bit of calcium-rich plage in there, but not very much. These tend to be very, very dark in color, and they have a low viscosity, which means they flow really, really easy. Now, mafic rocks start to lose the high olivine content, and they add other minerals like amphiboles and biotite to the mixture, as well as calcium and sodium rich plage that are kind of intermediate, starting to get to that intermediate. It's going to be more calcium, but you're starting to add a little bit of sodium in there. Ultramafic and mafic rocks tend to be very dark in color, like I said. This one also is going to have a low viscosity and will flow easily. Intermediate igneous rocks typically contain between 52 and 63% silica content. So, in between. Here we lose olivine completely and we start adding quartz and K-spar, as well as increasing the amount of sodium-rich plage, biotite, and amphiboles, while increasing the amount of pyroxene. Here we start to see the addition of muscovite, which is another type of mica related to biotite. The color tends to be a mix of light and dark minerals, like you can see in this one. And finally, we have felsic rocks, which contain more than 65% silica content. They're primarily made of quartz, K-spar, and sodium-rich plage. There are also smaller amounts of both mica and biotite. Mica. Biotite is a mica. I mean micas like biotite and muscovite. I can speak. And there's still a little bit of amphibole left. These igneous rocks are much lighter in color, and they are also really viscous and resistant to flow. So they're going to look very, very different when they come out of the volcano. That's all I have for you today on magmas, but make sure you tune in tomorrow for some Trivia Tuesday, and I will fossilize you later.